Ever wondered how a tiny glass bulb or plastic dome can instantly turn invisible electricity into visible light, without fire, fuel, or moving parts? Today on Knowledge Hub, we break down how light bulbs actually work by diving deep into the physics, materials, and electronics that make illumination possible. It all starts with electrical energy flowing from your power source into the bulb, but what happens next depends entirely on the bulb type. In traditional incandescent bulbs, electricity is forced through a very thin tungsten filament, and because tungsten has high electrical resistance, the electrical energy is converted into heat through resistive heating. As the filament temperature rises beyond 2500 degrees Celsius, it begins to glow, producing visible light through a process called incandescence, where hot objects emit electromagnetic radiation. The glass bulb is filled with inert gases like argon or nitrogen to prevent the filament from burning up. But despite this clever design, nearly 90% of the energy is lost as heat, which is why incandescent bulbs are inefficient and short-lived. Modern lighting shifted away from heat and toward direct light generation, and this is where LEDs, or light-emitting diodes, completely changed the game. Inside an LED, electricity flows through a semiconductor made from materials like gallium nitride, forming a p-n junction where electrons and holes recombine. When this recombination happens, energy is released directly as photons, a process known as electroluminescence, meaning light is produced without extreme heat. The color of the light depends on the energy gap of the semiconductor, while white LEDs use a blue LED coated with phosphor materials that convert part of the blue light into a broader spectrum that appears white to the human eye. Because LEDs are sensitive to voltage and current, they also contain driver circuits that regulate power and heat sinks that pull heat away from the semiconductor to protect efficiency and lifespan. Compact fluorescent lamps work using yet another method. Inside a CFL, electricity excites mercury vapor inside a sealed tube, causing it to emit ultraviolet radiation. This UV light then strikes a phosphor coating on the inside of the glass, which fluoresces and converts the invisible UV into visible white light. This gas-discharge process is far more efficient than incandescence, but requires electronic ballasts to control current. That explains why CFLs take time to reach full brightness. Across all bulb technologies, brightness is controlled by current flow. Luminous efficacy measures how efficiently electrical power becomes visible light, and color temperature is tuned through filament temperature, phosphor chemistry, or semiconductor design. So the next time you flip a switch and a room lights up instantly, remember, you are not just turning on a bulb, you are triggering carefully engineered physics, electronics, and material science working together to convert electrical energy into photons in milliseconds. If you've enjoyed this deep dive into the hidden technology inside light bulbs, don't forget to subscribe to Knowledge Hub for more deep dives into the tech that quietly powers our world. And as always, stay curious.